Hello everyone. In this lecture, I will discuss regarding LTE, that is long-term evolution. So far, we have discussed till Universal Mobile Telecommunication System, also known by the name WCDMA. In our last lecture, we discussed about that. Today, we will discuss about long-term evolution. So, what it is a project name given to the development of high-performance air interface for cellular mobile communication system, and it's a step towards fourth generation radio technology. So this is the whole evolution chart you can see in WCDMA starting from 2000 onwards. So this is the timeline and this is the system performance. If you can see WCDMA, then HSTPA, this is some improvement in the same technology. In WCDMA, there is an improvement over the downlink. So here the download speed is more, and later they improved upon HSDPA and then did some modulation, variation, and coding variation and all, and then achieved a kind of an uplink speed as well. That is by the name HSUPA, and then comes the transition phase. So this is all the evolution in the third generation, starting from WCDMA till HSUPA. Then many of the organization, particularly six organizations, are their names are not important. They came together, and they came together even before 2000, even third generation. All the evolution is under their supervision. That organization is 3GPP, that is third generation partnership project. That includes six, I think, if I'm correct, six organizations are there which are the part of third generation partnership project, and then they want to evolve and kind of a smooth transition towards the fourth generation. And so for that purpose, they gave that project name long-term evolution, which would be compatible with with the evolving technologies. So that we will see how they came up with LTE, what are the user requirement, what is the system requirement and all. So let's begin. So this is what the background I have already discussed about the third generation partnership project. So there was a requirement uh, regarding after third generation, there was a requirement that there must be some sort of a technology which would be compatible with IP-based internet, which would smoothly run all across the platform, all across the devices, and which would be compatible with IP-based technology. So that was the initial requirement, and from the application perspective, or could we say like users perspective, because users will eventually use the application. So from application or the user perspective, you will see the requirements are uh, because mostly over a period of time, many of the applications are data driven, and for that purpose, you require higher data rates, which were not there in even in third generation, because the applications were evolving, and those application demands higher data speed so as to function. So for that purpose, the user perspective, you will see the requirement is higher data rate, more throughput, lower latency, and this is important, the last one, that always on connectivity. So even if you are on voice call or any other functionality you are using, but still all the application which are data driven uh, should be on, and it is not all about on, there must be a connectivity, then only those applications can run. So there is an always on connectivity requirement as well. It is not with there with GPRS. If you will see, in case of GPRS, GPRS also support to data applications, but there, if you see, uh, even if someone, so any one of these two operation you can use. If somebody switches from data to voice communication, so if you are using your mobile device for voice communication, at that time applications would stop. They will not use the packet switched network for their data communication. But that requirement no longer, you can't stretch it. You have to change it so as to support the applications and user requirement. Then from the operators or from the business perspective, you will see the requirements are also important. And the first requirement is that there must be an efficiency on a ground of power and bandwidth. So efficiently, we must utilize the power resources wherever it is, whether it is at the user equipment or the base stations or the node B you are using. So on whatever level we are using power, it must be efficiently utilized, and the bandwidth, whatever been allocated to us, should also be efficiently utilized. Because till that time there were several other technologies as well, so there was always a requirement that the new technology must be compatible, or to say that not only backward compatibility, but the option is that all these things over a period of time in future would converge, and uh, only one technology prevails. So that was also somewhere in mind, uh, who were designing and who were thinking about the future perspective. So from the operator's perspective, you will see if there is a sort of a consistency in technology, people can invest in that. So it is to facilitate the convergence with other network technologies. Then obviously these requirements are also there, that the transport network cost. So per packet, whatever you are transporting, the overhead charges should be less. Overhead charges may be in terms of time, you can calculate processing time, you can calculate congestion, so many ways of calculating, but the network cost should be minimum per packet, or rather if per bit, if you are calculating, it should be less. And whatever we are expecting, that is also one of the requirement, that whatever at that time those people were expecting, the requirement is that whatever the design and architecture is there. So because over a period of time, the design till second generation, from second generation, from second generation till third generation, if you will see, these things evolved over a period of time. So as and when anything or the new generation requires, based on that, there is an add-on features. They added it both in terms of physical or hardware or in software. So over a period of time, it's a sort of an amalgamation of several new things, and that leads to complexity. So the requirement is that from scratch you can design the fourth generation, but it must be simple. There must be a simplicity in its design. Simplicity, to put it in a technical way, simplicity means so that the control plane and the user plane. So there must be a distinction. There must be a well separation in control plane and user plane. Now, what is control plane and user plane? If you see, then control plane and user plane is related to the applications which are generating data, which you are going to forward. So obviously for all that purpose, you also require protocol. So there is a set of protocol which will deal with the user application and user data to forward and process it and all. And the second one is, even for all these functionalities to happen, there is a control section, there is a control plane which will control. So there exists protocol which will control base stations, which will control a kind of interaction in between several network entities. So there must be a valve separation, so that if there is any change in user plane, that would not impact the control plane. If there is any change in control plane, that's not going to impact the user plane. So kind of modularity, you can say that it must be highly modular in its design architecture. So that was also one of the requirement. And the evolved one is the evolved one, this evolved UTRA. This UTRA is UMTS, Universal Mobile Telecommunication System, terrestrial radio access. So radio access network, it's a radio access network, which we know in case of our last protocol WCDMA with by name, the same name UTRA, and radio network system RNS. So it is the same thing. But here in our all previous technologies, that radio network subsystem was supporting circuit switching as well. But here this evolved one, so evolved UTRA was supporting in the previous case. If you will see, the UTRA in previous WCDMA or UMTS was supporting circuit switching and packet switching both. So there was MSC as well as involved. So whenever there is a requirement of circuit switching, it was happening through mobile switching center. Wherever there is a requirement of packet switching, it was happening there with the help of serving GPRS support node. Whereas there is no point. I mean, it is almost scrapped. This design is almost scrapped MSC. So there is no circuit switching at all. Yeah, it is compatible with backward technology, with circuit switching. If any of the previous technology wants to interact with it, there is a whole mechanism, there is an interface over which it can interact with it. But in its own design, it's not going to implement circuit switching as such. So that is good part about this. And so in the third generation partnership project, so in this project, uh, there were two modules. So one module of study was regarding radio access, and that is also known by the name third generation long-term evaluation. That is for radio access. That is for radio access system. So what kind of radio access system our fourth generation is going to use? And the next one is the core architecture, because the requirement is now we have to simplify it. So on both levels, there is a requirement of changes. There is a requirement to change both your radio access network as well as the core architecture, the core design itself. So in third generation, in this long-term evaluation project, uh, the third generation LTE, so long-term evaluation, one group was there for framing and for bringing out the requirement and the design regarding the new radio access technology. And the second one is that how this radio access technology is going to be interacted with other technologies through core architecture, through the core network. So that is also known by the name evolved network. So that group which was formed by the name system architecture evolution, or system architecture for evolved network. So this is what the background is. Now these are the requirement and performance targets. So obviously the requirement in terms of higher peak data rates, so spectrum efficiency already we have seen, but so the in LTE, so these requirement being crystallized. So these are the requirements, certain requirement, but I'm just broadly in a very abstract way, I'm just going through all the requirement that obviously the peak rate should be high. So this concrete information is given. You can see 100 Mbps and 15 Mbps. These are the requirement it should support. It should be adaptive in nature. It should support either 50 Mbps, 100 Mbps. So these are the peak data rate it should support. Now the improved spectral efficiency. So whatever being on the spectrum given to us, that must be efficiently utilized. Then it must support several bandwidth requirement, 1.4 megahertz, 3 megahertz, 5, 10, 15. Then improved cell edge rates. These edge rates are related to the coverage. It is like that if the edge rate is more, then the coverage will be less. If the edge rate is less, the coverage will be more. So I'm not going into the specificity of the edge rate, but it is to deal with the coverage. So the requirement is that there must be a full broadband coverage. So then the low latency, and as now it is going to only deal with the backend domain. So these are certain specific performance requirement and the targets. Now, how these targets are going to be achieved? What is new in LTE, which is differentiating it and allowing this new technology to achieve all these set performance targets. So these are the three specificities which are associated with LTE. These are improvements. One is on the radio access platform. So on the air interface, there is a selection of orthogonal frequency division multiplexing. And just by the choice of orthogonal frequency division multiplexing, while discussing multiplexing, I discussed about the orthogonal frequency division multiplexing. So different users will be given orthogonal frequencies. So orthogonal frequencies have been chosen in such a way that uh, when you condense, when you bring all the frequencies together, so the peak of one will coincide with the minimum of all, with the zeros of all. So it is easier for anyone to distinguish its own frequency. So that is the properties related to orthogonal frequencies. So that is going to be used here. And what are the additional advantage of using orthogonal? Uh, the requirement at the receiver end, because if you are going to use the complicated modulation technology, so obviously your receiver will be complicated to decipher it. Here it is so simple. So the receiver complexity goes down just by the use of orthogonal frequency division multiplexing. Then ISI, inter-symbol interference, is also low just by selecting the right orthogonal frequencies. It is highly robust just because of this. And just by the use of proper orthogonal frequencies, you can meet this demand. The demand is that it should support different bandwidth. So maybe certain application require only 1.4 megahertz bandwidth, certain application require 10 megahertz bandwidth. So based on application and based on whatever your requirement, the requirement is that it should support what technology. LTE should support the scalability in terms of the bandwidth availability. So that we can just materialize through the use of right selection of orthogonal frequencies at the right time whenever we do require the frequencies for transmission purpose. Then the second requirement, the second key feature is the integration of multiple input, multiple output techniques. As we know through reflection, scattering, uh, which we have understood in terms of attenuation. So that is a sort of a negative thing, because if your signal is going through a multiple reflection, eventually it will reach there, but there may be a phase shift. So many issues may happen. But here, through multiple input and multiple output technique, this negative things, this negative feature, this negative uh, aspect which comes out of a reflection, uh, we want to turn it into some positive feature. How? uh, we will take all these phase out signals, and we will then phase in all these signals, we will boost the signals, and then we will use those all signals for our good purpose. So this is in a very crude way put it up. There's a specific way how to deal with the signals which come out of reflection scattering, and instead of just negating those signals and filtering out those signals, we will somehow make good use of those signals which could be at our disadvantage. We want to put those signals for our advantage purpose. So that is the technology MIMO. And then already I have disclosed that here, while implementing the design per se, while implementing the architecture, they've taken out several features because even the requirement is also less. Now the requirement says that you have to deal with packet data. You don't have to deal with the voice data as such. So the requirement is also less, and from scratch they could have proposed the design architecture itself. And for that purpose, they first initially distinguished the control plane and the user plane, came out with the protocol which support control plane and the user plane, and then put it all across the design. So there is an omission of several logical nodes. So there is a reduction in the number of logical nodes, and that's amount to flattening the architecture. So this is what the timeline is. So it's a sort of this LTT is a revolution in the design itself. Because over a period of time, third generation, we were just evolving, and the use of OFDM is a sort of a revolution in the design architecture. This is what the timeline is. This is not that much important. Now we will discuss about the architecture. So in one thing is that only because it is not going to support on the circuit switching, so that's why LTE would not be backward compatible with UMTS or HSPA. So it is not backward compatible only because it is not going to support, but it is not so that it won't be interactive with it. So there is a distinction in interaction, whether it is interactive with the technology or is it backward compatible. It is not backward compatible, but still through a proper interface. I will let you know later on that there is a proper interface through which it can be interactive in its design. So in its design, it is interactive with all other protocols per se, but it is not backward compatible. So this radio access network working group. So there are two groups as I mentioned. There is the radio access network group where the entire focus was on radio access network aspect. And then they came up with the choice of OFDM and MIMO. So these are the choices. Now the third one is, the second one is the system architecture group. And their task is to flattening the design, take out all redundant nodes, and there must be a clear distinction in control plane and user plane, and then come up with a design. So for that purpose, there is a system architecture group which work towards evolving the evolved packet core. So this is the name given to that core architecture, evolved packet core. So there is a word, so you will often see the word E. So the E here means the evolved one. So anything like the node B. In case of third generation WCDMA, we have seen the node B. Here you would see E node B. So evolved node B. Likewise, here you can see that this evolved UMTS terrestrial radio access network. So whatever the radio access network, uh, which we have seen in case of UMTS with the name Radio Network Subsystem, RNS, which is two-part network, radio network controller, and Node B. Here the same thing, they have evolved, uh, they have done something to it, both in terms of hardware and the physical presence of the entities involved. So that is known by the name EUTRN. Whereas till the third generation, the name was just UTRAN. And it is also known by the name long-term evolution, LTE, which is generally used interchangeably. The software architecture evolution, the software group evolved the core architecture with the name system architecture evolution. So for some time, this architecture and this design, this technology is known by the name LTE oblique SAE, but over a period of time, they converge and start using the word EPS, Evolved Packet System, because this technology is compatible with IP-based technology. Now here you can see in the network simplification how they simplify it from third generation to the fourth generation LTTE. So the name is just 3GPP, but it is the fourth generation LTE because this is an organization, third generation partnership project. So under that, there is a project LTE, and under 3GPP, they started with WCDMA, then evolved it to HSDPA, then HSUPA, and then over a period of time, then to LTE, then after LTE, to other fourth generation thing, and now under the same organization, 3GPP, 5th generation work is going on. So under this, you can see initially here, there is no clear separation in case of control plane and user plane with respect to third generation technology. So here with respect to WCDMA or any of other third generation technology, if you would see, then node B is interacting with RNC. It is a radio network controller, which is a part of radio network subsystem, or UTR, this UTRAN, Universal UMTS Terrestrial Radio Access Network. So this RNC is the part of that. It is interacting with node B. So this is the signaling channel, and this is the normal traffic channel. Signaling channel means control channel, and traffic channel. So here you can see. So then this RNC is under control of serving GPRS support node. And this serving GPRS control node is in contact with gateway GPRS support node to contact the external world, the external internet. So here you see there's a 4 functional entities, and to handle those 4 functional entities, how many interfaces are there? You have 3 interfaces. So 4 functional entities on the control plane and user plane, and there you require 3 standardized user plane and control plane interfaces. So these are the control plane interfaces. These are the, so they, because there is no clear separation as such. But here when they evolved it, so this is the evolved design. So in this evolved design, you will see that there is an evolved node B, which took certain certain functionalities. So now there is no distinction in between node B and RNC. RNC is a part of radio network subsystem, which is nothing but UMTS, terrestrial radio access network. So RNC controls several node Bs. So RNC has a controlling feature. So that controlling feature, now individual cell, in case of the evolved architecture, you see individual cell would have only one E node B. Node B is nothing but a base station, which we all know by the By now, I think you must be familiar with the base station. So Node B is a new terminology. In our last class also we have seen Node B is equivalent to the base stations, which been controlled by now till the third generation through RNCs. Now, in case of the evolved architecture, uh, Node B has some part of the controlling features. The control plane, some part of it would be the part of eNode B. So here you can see in the LTE architecture, there's a two functional entities. So you can see broadly there, these are the two functional entities, eNode B and serving gateway. And within serving gateway, there is a mobility management entity. So in total, three entities are there. MME is a part of serving gateway. You see, so two functional entities are there. And to interact in between these two functional entities, you require two interfaces, one traffic interface, one control interface. That's it. Traffic interface is corresponding to your user plane, and control plane is respect to the control plane you require. So there is a requirement of less interference, less interfaces. So some functions will also disappear. So four layers, these four layers we have condensed into two layers. So uh, this evolved GGSN is now integrated and is the part of. So this functionality, it is color coded as well. You can see that the functionalities of GGSN is shown by this color, blue color. So you can see that majority of or many of the functions which GGSN was doing now it is under the custody of serving gateway itself. Likewise, SGSSN, it is also now the part of SGSW. RNC, some part of it is there in software, serving gateway, and some part of it is now under the charge of eNode B. Like evolved, moving SGSN functionalities to SGW, RNC evolution to RRM on an IP distributed network for enhancing mobility management. RRM is nothing but radio resource management. RNC is radio network controller. So when you evolve and this functionalities goes to radio resource management on an IP distributed network for enhancing mobility management. And part of RNC, as I have mentioned, move to SGW and some move to Node B. Now we will see the interaction, the whole gamut regarding the evolved UTRAN architecture. UTRAN stands for Universal Mobile Telecommunication System, that is UMTS, Terrestrial Radio Access Network. So there is a user entity, user device, user equipment. Then user equipment is interacting with UTRAN. UTRAN is interacting with the core architecture. Then core architecture is facilitating further connection to the outside world. So this is the whole layer of interactions. So this UTRNA, if you will see, so here in the evolved design, in the evolved UTRAN, in the evolved one, there is no RNC at all. Whereas in case of the third generation device, in the third generation technology, we have seen there is a requirement of RNC. There was a unit by name radio network subsystem. Within radio network subsystem, there were two entities involved. One is controller, another one is Node B. Node B is nothing but the base station itself. So several base stations were there in the under the custody of radio network controller. But there is no concept here of radio network controller. Individual node has some controlling power itself. So this Node B or the base station, which will monitor the radio resources, to allocate the radio resources. So radio resource management, majority of the work is now given to evolved Node Bs. Now these node Bs are directly interacting with each other over the interface X2 for seamless mobility and interference management. And these node Bs are interacting with this, because this is the entity which has a subpart with the mobile management entity, and so SGW, there is only one entity now, because now we have condensed everything into two entities. One is node B and another one is serving gateway, and this serving gateway has one more part, that is mobile management entity. uh, with the name itself, it is explicit in its operation, that what operation it's going to play out, and then mobile management. So here you can see the interaction over the interface S1. So this one, software gateway and MME. So this is the part of evolved packet core. This is the part of core network design, and this is the part of evolved UMTS radio access network. Now we will see this evolved uh, packet architecture, EPS architecture, with functionalities. What are the functionalities of individual node? So the entities, now just remember, there is an evolved node B, which is nothing but the base station. This is serving gateway, which we have seen that it is nothing but whatever the functionalities comprises of GGSN, SGSN, and some part of RNC, which we have condensed, squeezed together, and now that is the part of SGW, keeping control plane and user plane in mind. So we have designed our protocol in such a way. Now the protocol stack, we will see how they have designed. Now, if you will see, so this is E and B is a part of your evolved UTRAN, that is evolved UMTS radio access network. So because there is only one entity now involved. So what are all its functionalities? Evolved node B contains all radio access functions. So whatever the functions which account for radio accessibility, those all the part are there in its functionality, like admission control, who will be given admission, whom will be allocated radio resources, so that admission control, when you have to schedule upper link data and the downlink data, so that scheduling, and the scheduling of paging and system broadcast, paging operation, system broadcast, how to schedule it, that functionality is also there with evolved. And because as I have mentioned that the whole protocol revolves around the IP, it is compatible with IP based other technology. So this evolved node B would do the IP header compression. So whenever a packet would reach the electronic, not sorry electronic, it is evolved node B, it will do the header compression. And this radio link control, that is at the logical link control, it will do the retransmission using automatic repeat request, ARQ protocol, using ARQ protocol. It will use one more protocol, that is higher end ARQ protocol at the MAC layer as well. So two times, so just to ensure the higher reliability towards higher, and we are using two ARQ protocol. One is a normal ARQ protocol, and another one in the MAC layer also we are going to use the higher end ARQ protocol. So here other functionalities you can see, that the inter-cell radio resource management. So within one cell or with other cells, so radio resource management, that functionality is also been given to evolved node B. Then resource block control. Resource block is nothing but the application data. So whatever be the application data, application, the node will evolve, will give the data packet. So how to control that, means header and all. So resource block control. Connection mobility control, so setting up the connection, that feature is also there. Radio admission control means it is all related to the radio resource management. So all other functionalities are related to radio resource management. Then this radio resource control, this RRC is also there with respect to radio radio resource controller. So this RRC is the radio resource controller, which is self-evident that you do require one protocol which will control the radio resources. So for that purpose, you require radio resource controller. Then PDCP, because here uh, in this technology is going to be highly interactive with other technologies outside itself. So during that time, it's going to interact with several of the protocol which are not the part of this technology. So for that purpose, you require some convergence protocol which will converge. So whenever you will interact with other outside world protocol, how will you converge and bring it back into your domain? So for that purpose, there is a PDCP protocol, Packet Data Convergence Protocol. Then you have radio link control. This radio link control, as I have mentioned, so this radio link control and MAC control, we know that in the TCP/IP protocol module also we have these protocols, radio link control and MAC control. So it is compatible with IP-based protocol design, radio link control and MAC layer, and the physical layer. So physical layer for the same operation as we have stated in case of the IP-based protocol. Now it is going to interact with the core architecture. So this is the radio network environment. Now over the ASVER interface, it is going to interact and interface with one is your MME, which is the part of serving gateway, and then so there is a serving gateway, and there is a PDN, public data network gateway, which will interact eventually with internet. So if you will see and draw the parallel with respect to MSCs and gateway MSCs, though which were there for circuit switching. So the serving GW is with respect to mobile switching center, and PGW, just to draw the parallel so that you can easily understand, this PGW is in correspond to which will interact on the gateway MSC. So this PDN is or with packet switch to environment, if you will draw the parallel, then SWGW is in correspondence with the software or software serving GPRS support node, and this PGW is in correspondence with the gateway GPRS support node. Now this MME, we will see that these are certain control plane functions, mobile management entity. So whenever mobile will be mobile, so from here and there, how it's going to manage, let's see. So it will look for the idle, if suppose if there is any user device which is sitting idle, is not doing an idle, so it will reach to that node. So it will figure out where exactly which node is serving it. Initially, if there is a node which just joined, there is a mobile user device, user entity with just user equipment which just joined the network. So only through MMEE. So this MMEE will interact with there is one home subscriber server, so which is a part of internet somewhere, home subscriber server. This MME will interact with that home subscriber server for figuring out the authentication information, and then will attach it. And while attaching, it will assign one as GW, serving GW. So all these functionalities are bestowed to and given to MME entity. And then it will track the area list management. This we have discussed that SGW and PGW selection during attachment into the reverse of a detachment also. Then inter-core network node signaling for mobility between 2G and 3G and LTE. So because when you will be mobile, sometime you will be in that environment where you can only access 2G, sometime you may access 3G, sometime LTE. So this MME will take care of all these things. So when you are going to access 2G, 3G and LTE, so it will do the kind of a signaling which will alert the system so that you will use the right kind of technology which is available and supported by your device. And then NAS signaling authentication, authentication the very first time when your system is going to be attached, your device is going to be attached, and in meanwhile also then bearer management functions. So NAS, what this NAS is, it's a known access stratum. It is used to convey known radio signaling, known radio, not the radio signaling. So this NAS is known access stratum, which is used to convey known radio signaling between the user equipment and mobility management entity for LTE oblique EUTRAN access. So if you have to convey anything which is non-radio in nature, so for signaling that purpose, we use the known access stratum. And this SGW, here you can see what this SGW will do. So this SGW will handle the local handovers. So when one device will move from one SGW to the next SGW, so it will handle this local mobility, it will anchor this local mobility for evolved node B handovers. It will also anchor the mobility anchor for inter 3 GPP handovers. So inter 3 GPP handovers means you have a third generation technology. There are several things: WCDMA, HSPDA, HSPA. So many other technologies are there. So when you will move, you will be mobile, and when you will move from one location to another location, it may be possible that you have to switch from one access technology to the next one. So for that purpose, this serving GW will take care of those things. This MME will alert SGW for doing that. Then in idle mode, if your device is idle, at that time, if there's a certain packet which being destined to you, but you are idle, HGW would not be able to hand it over to you. It can buffer those packet. That work is being assigned to SGW. Low full interception, obviously everything is going through SGW. So if low allows you to do that, if somebody asks, any organization asks you to do that, you can do so because everything is going, every packet is moving from SGW. And obviously it is a gateway, means it will also act as a switching device as well as a router. So for that purpose, packet routing and forwarding will also take place through SGW. As we have seen that uh, this SGW comprises of gateway GPS, gateway GPRS switching node, and serving GPRS switching node. All the functionality is being condensed in SGW along with certain features which are the part of SGSSN and RNC that comes together and termed as MME, Mobile Management Entity. And this PDN is nothing but this PDN gateway. It is used for allocating IP addresses. So whenever you will move to any network, so MME will first attach you with one PGW, and that PGW will give you will allow you to use a certain IP address which will assign to you through PDN gateway, and it will anchor. Now, it may be possible that you want to interact with GPRS network. You want to interact with GSM, which is not the part of 3GPP. So in that situation, how that thing would be feasible, as I have told you that it is not a backward compatible, but still it is interactive in nature. It will allow you to interact with all other protocols, all other technology as well. So that we will do through PDN gateway, and obviously which is important that it is going to give you a kind of connectivity to the packet data network. Now this bearer management function, what this bearer management function is there from user device, if you will see, because behind even evolved node B, there is a user device, and from user device, user wants to interact with the internet. So you require a kind of a logical tunnel. So that service who is going to provide that logical connection from the user agent, not user agent, from the user equipment to internet. In between, so many things are there: evolved node B, MME, SGW, but the user wants a kind of an abstraction, and in that abstraction, it want to just follow it up to all these things which comes in between. So who is going to do that? So MME is going to do that, and it will create a sort of a pipe, a logical pipe, which will connect directly the user equipment to internet. So that is the part of peer management functions. And now we will see that how protocols will interact, what is the protocol stack and all. So EPS architecture control plane layout over interface S1. Over this interface S1, you can see this is user equipment, this is evolved node B and MME. So user equipment will first interact with the evolved node B, that is the base station itself. Then this base station will interact with SGW, and within SGW, it will interact with MME, mobile management entity. So here you can see this NAS, this NAS sublayer function says, so NAS is user equipment is directly interactive with MME through NAS protocol. So this NAS, so what this NAS sublayer performs, it will do the authentication function. How it will do the authentication function? Means any other protocol, I'm not naming the protocol. So when you will design a protocol at NAS, you have to share with MME your authentication information, whatever the authentication way you are using. Once you will share this information with NAS, here this MME will interact with the outside, somewhere over the cloud. There exists that home subscriber server. So that home subscriber server has all this information. Then it will interact with, so there, that is the interface name as 6A. Interface is not important. So it will interact with that home subscriber server, and from there it will confirm. Security control same way. Then idle mode mobility handling, and idle mode paging origination. So these 3 or 4 operation you have to manage through NAS layer. Now this RRC is a radio resource controller. So all the features which are associated with resource allocation, deallocation, handover, and all these things being governed through RRC. And who are the parties which are going to interact? It is directly the evolved node B, which is responsible for resource allocation, deallocation, and over all these things. So your user equipment is directly going to interact using RRC layer with this ENB. So these are the operation: broadcasting, paging, connection management, radio bearer control, mobility function, and measurement, reporting, and control. So these operations, so which are somewhere related to resource allocation, radio resource allocation. Then convergence layer, already I have disclosed about that. When you are interacting with any outside protocol, at that point you require some mechanism to converge it back to your way of scheme. And along with that, here we are using the integrity protection and ciphering. Any ciphering operation, any key operation over the data if you are doing. So for integrity purpose at PDCP, we will do it. Then you have RLC layer, MAC layer, and physical layer. You know the operations, but just let me brief you about RLC layer. So along with that operation, integrity protection and ciphering, at PDCP, you will do the header compression as well. While discussing about the evolved node B, I mentioned about that it is going to compress it. How it is going to compress at PDCP sublayer, it's going to compress the header, and ciphering we have understood. RLC and MAC, these are the part of data link layer. Because it is compatible with IP-based protocol. So from one device to the last device. So suppose it may be possible that you are using LTE or VoLTE, but with whom you are interacting with the server, which is a part of IP-based protocol stack. So how you will interact eventually. So you have to have some MAC layer and RLC layer as well. So this RLC is what it will do, it's a normal operation as usual in IP-based protocol it does. So it will transfer the upper layer PDUs. It will ensure in-sequence deliveries of PDUs from one hop to the next hop. It will ensure the error correction through ARQ, so reliability, duplicate detection, flow control, segmentation or concatenation of software, STU, uh, data unit, software data units, and these are the protocol data units. Then the MAC layer, you know, to access medium access. So for that operation, here also we are doing the error control through higher end some ARQ protocol, and so whatever the functionalities we know at the MAC layer is going to be performed at this layer. Physical layer, here we are using for downlink OFDM. For upper link, we are using single carrier FDMA, which is a variant of OFDMA. Just the name is different, single carrier frequency division multiplexing, though even OFDMA is a sort of a special frequency division multiplexing where the selection is important, what kind of frequency you are selecting. Frequency should be orthogonal in nature. Likewise, in single carrier FDMA, which is also one variant of OFDMA, which is used for upper link. And forward error control, uh, upper link power control, because when you have to upload anything, we have to think about power control as well, and the inception and the usage of MIMO for our advantage. So multiple stream transmission and reception, that is MIMO, multiple input, multiple output. So something which was uh, at our disadvantage, we want to use it as our advantage purpose. That is all. Now this is the EPS architecture. When it will internetwork with non-GPP access network like GPRS. So here, this example you can see. So this is the EPS core, Evolved Packet Network. This is the core, serving gateway and PDN gateway. This is what the core is. Then you have MME, which is the part of serving GP, serving gateway, MMEE. And this PDN gateway will allow you to access non-GPP access network. So, and it is directly connected to internet also. Now suppose how you will interact. So serving gateway. So serving this serving gateway, you can see this serving gateway anchors mobility for intra LTE handover between evolved node Bs. We have already discussed about this, as well as mobility between three GPP access system. This also we have discussed that if you will transit from HSPA to Edge to any other GPP, so it will anchor it out. So uses EPA core for access to packet data network. Now this PDN, what this PDN is responsible for, this also we have discussed. It is just through graphical representation through this picture. Once again, we are discussing PDN gateway node is the mobility anchor between 3 GPP and non 3 GPP access system. So it also handles the IP address allocation. Now this MMEE, so as I mentioned that how it will ensure the backward interface. So if it has to interface with GPRS. So as we know that GPRS has serving GPRS support mode. So our MMEE in LTE would interact over the S3 interface to that serving GPRS support node. So S3 interface connect MEME directly to SGSSN for signaling to support mobility across LTT and UTRAN. UTRAN is the part of WCDMA, or another name is UMTS, and GERAN. So S4, now once it is done, now this S4 allows direction of user plane between LTE and GERAN, and UTRAN uses GTP. That's all. It's not that much complicated. That idea is that through MME using two interfaces S3, so you would interact with serving GPRS support node, which may be the part of WCDMA, which may be the part of GPRS. So then onwards, this MME would interact with the serving GPRS, this over the serving GPRS over the S4 interface. These are certain more key features, the radio features. So multiple access scheme, what kind of multiple access schemes we are using. At the at the download link, we are using OFDMA with the cyclic prefix. This is not important, just remember OFDMA. And for upper link, we are using single carrier FDMA with cyclic prefix. So it support in its radio feature LTE support an adaptive modulation encoding technique. So over the download link, it support several modulation schemes: quadrature, phase, shift keying, 16 quadrilateral, amplitude modulation, 64 QAM. So any of these variant, depending on the requirement, we can use it. It is adaptive in nature. For upper link, QPSK 16 and this. Then there are different coding techniques, the channel coding techniques. ARQ and hybrid ARQ. So ARQ is associated with RLC layer and hybrid ARQ is associated with MAC layer. I've discussed about the importance of MIMO as well. So this advanced MIMO, so this ARQ is for reliability purpose, so that you can retransmit it. So if anything not been reached at the destination, the next hop correctly, there is some certain error and all, so you can once again retransmit it. So for that purpose, at RLC, we are using automatic or repeat request ARQ protocol. At the MAC layer, we are using hybrid ARQ protocol. So then at the physical layer, we are using MIMO. So in these variants, 2x2 or 4x4 downlink and 1x2 or 1x4 uplink it support. It support implicit interference coordination, and it has in the last case also, in case of WCDMA, that was also supporting FDD and TDD, and this technology LTE also support both frequency division duplex and time division duplex. This division duplex is for one is uplink channel and another one is downlink channel. So on what ground? If you have large frequency set, then obviously out of that large frequency set with certain gap, you can have one frequency associated with uplink and another frequency associated with downlink. So exactly at the same time, you can support both the operation uplink and downlink with certain filters you do require, those are necessary. Whereas if the frequency requirement is less and still you want to use, so the same frequency can be used for uplink and the same frequency can be used for downlink, where the division would be on time scale, on time slots. So if you divide the time in different time slot, so some time slot would be for uplink operation, and sometimes slot would be for downlink operation. Then your transceiver, you have to sync in accordance with that time division. That's all regarding LTE. Now there is just a minor difference in case of volt. So where the idea is that convert your voice also in data packets, and those voice packet would then also use the same network architecture. So the name itself suggests that voice over LTE, because this LTE is specifically designed for data operation, for data communication. Now, VoLTE is to support even the voice communication over the packet switched network. Because so far, even in all third generations, what we have done, we have used two operations, two ways. One is for voice communication, another one is for data communication. But as we know, this LTE is exclusively for packet switched network. Now there is no scope of voice communication therein. If you are not, until you are not converting and digitizing your voice and converting it into packet form. So VoLTE is nothing but voice over LTE. So that is not that much. So that much understanding is enough, because more or less the architecture is same with certain minor variations for supporting voice there. But more or less, so the design architecture, the evolved packet system is entirely same. That's all regarding LTE. In next lecture, I will discuss regarding wireless LAN and then ad hoc network. Okay.